So, welcome. My name is Christine Shupla. I'm with the Lunar and Planetary Institute. I work with Andy Shaner. He's out for the next month. So, I am filling in for him, but this program is not my program. I'm his manager, and so I'm not as experienced with this program as your teacher is actually. For this presentation, I want you to know that what you're saying, your presentation is not going to be graded. There's no grades here. It's not, the presentation's not part of the competition. It's a starting point to make sure that you have a good grasp of some of the key concepts. And so I'm looking forward to hearing you and hearing what you have to say. I will have questions for you afterwards, but those questions are not intended to imply or suggest that you don't know what you need to know. They're just sort of a way of testing you on different topics and getting you to react and hearing what you have to say. So, so please relax. Nothing that you're about to do is a test. It's not. It's not something that you are being challenged on right now. This is just the starting point. We're getting all the teams ready and getting them lined up and making sure everybody's got their sneakers on and their shorts. That's pretty much where we're at with this. So.
And I think it's a great experience before you have to do the competition presentations and things to get your feet wet.
So breathe deeply, everything's fine. I'm really looking forward to hearing what you have to say. And I'm a little bit new at this too. My understanding of planetary science is fine, but I'm a little bit new at listening to these presentations. So you're only the second group that I'm listening to so far. So.
All right, so we'll share screen. Assume it's gonna work just like
this program works just like Zoom.
That's good. So we are going to start, and we're going to start with Nathan in just a second. You're going to do, unfortunately, Nathan couldn't be with us, but he's doing the introductions because he wasn't able to rehearse here, but I think he's ready to go. All right. Okay. Oops, why did it do that? I thought I had the beginning, so I guess it didn't quite work like I thought. There we go. Okay, go ahead, Nathan.
It's still not at the beginning for me.
Yeah. Oh, it's getting there. There we go.
Okay, there we
Holly,
go.
I think your computer is running a little slow too, so if you have extra browser windows that you don't need, I'd recommend closing them.
Okay. Let me see. I'm going to have to exit this to see.
What you could do is you could turn off your camera. I don't know if you can.
I can. Let me make sure I can turn that off, and I can turn that off so I just have the two presentations, and I can go back here. Good suggestion, Dylan. Okay, I don't want it that small. Okay. I can't get back now. Okay, I bet if I do this. Okay, meeting controls. I'm sorry, how do I get it so that I can get to my controls?
The control, I'm trying to remember.
Oh, it's got this thing here. Okay, I remember, okay. So I need to get down there so I have like, oh, there it is. Stop video. Okay, there we go.
Okay.
Good job, Dylan. All right, so now let's present.
All right, whenever you're ready.
Okay, I'm ready.
All right.
So, St. Mary's School. Yeah, Moon 101. Okay. By the St. Mary's Astronomy Club. They're all the names. What we will cover: theories on how the moon formed, geologic history of the moon, physical features on the moon, lunar missions, lunar image analysis, conclusion, and we're excited.
Ron.
Hi, my name is Tron. I'm gonna present on the theories on how the moon formed. Next slide, please. So the first theory that I'm gonna present, it's also the most popular theory on how the moon formed as of now, is the giant impact theory or the impact theory. So this theory hypothesized that an asteroid or a planet roughly the size of Mars has impacted the Earth during its formation, and this impact resulted in the rocky surface material being blown outward from the Earth and accreted to form the moon. So some of the pros of this theory is that during the formation of the Earth, there were frequent collisions, and so the likelihood that such an impact happened is possible. This also explained the moon's smaller iron core as the core of the Earth was changed during the impact. And there were a lot of simulation and models made by scientists that has confirmed the possibility of this theory. And this theory also explained the tip of the Earth axis. Two of the cons of this theory is that the impactor would need to be at the angular momentum that is now in the Earth-Moon system, and the collision could have made multiple moons, which is another possibility. Next slide, please. So these are some photos of the hypothesis and the simulation that was made. On the right, there were two models of how the Theia impact happened. And so the first model showed that the impactor produced a disk of materials around the Earth, and these materials they coalesce into the moon. On the right is another model that shows the impactor at the same around the sign of Earth, and this impact would mix the material from the impactor and the young Earth and produce a composition that is similar to the Earth and Moon. On the left, there is another simulation by a computer of how the impact could have happened. And so you can see that a part of the Earth's core is flown out, and therefore it might explain for the similar composition of the nickel iron core mantle of the Earth and Moon. Next slide, please. The second theory is the fission theory, and this theory proposes that the moon was a part of Earth, and as the Earth spins, a portion of it is flown into space, and as the molten part cools and rotates, the materials would form our current moon. And so the pros of this theory is that the density of moon is similar to that of the outer layers of Earth, and this explains some similarity of the rocks on the Earth and Moon. A con is that if this theory is true, then the material should be orbiting along the Earth equator, which is not true of our current moon. And there are still some dissimilarity between the rocks composition of the moon and Earth. So therefore, this theory might not be true. And also, for this theory to be possible, the Earth would have to be spinning extremely fast for the material to be ejected. Okay, next slide, please. And the third most popular theory is the capture theory. And this theory also supports some reasons for the moon's orbit and the tidal law. And this involves the Earth's atmosphere and gravitational pull that slows the movement of the passing moon and capturing it into the Earth's orbit. And the pros of this theory is that there's a possibility that this could happen because the Earth's gravitational field at the time is strong enough. And a con of this theory is that if this theory is true, then the rocks in the moon is unlikely to be the same on Earth, and this cannot explain some of the similarity of the composition of the Earth and Moon. And also, the kinetic energy must be carried away by a third body. So with the capture theory, no energy is produced. And this theory also cannot explain for the identical or similar isotope ratios between the Earth and the Moon, since there were no direct contact between both bodies.
Okay, so next part is geologic history of the moon. Next slide, please. Okay, lunar magma ocean. The lunar magma ocean is a layer of molten rock that is shearized to have been present on the surface of the moon. The lunar magma ocean was likely present on the moon from the time of the moon's formation, about 4.5 or 4.4 million years ago, to tens or hundreds of million years after that time. Okay, next slide. Next slide, please.
It is, but it's probably taking to load, I think, because it's that animation.
Okay. And this animation is showing the cross-section of the lunar magma ocean as it's crystallized over time. And the first solids to form are denser than the surrounding magma, and thus sink toward the interior. After about 80% of lunar magma ocean has crystallized, less dense solids begin to form and float towards the surface, forming the primordial crust of the moon. It's a thermodynamic consequence of the moon's relatively rapid formation in the aftermath of a giant impact between the proto-Earth and another planetary body. Yeah, next.
Okay. Talk about the summary of magma ocean. So lunar north side play a big role when we want to know the age of the lunar, because this rock crystallized directly from the global magma ocean. And isotopic and trace element composition of lunar north side provided better information. Before this study, other evidence showed a pretty huge range of the age. The range brings a big challenge for the moon made by the magma ocean. However, the range of the age reported by the previous study shows that the age of the earliest lunar crust maybe is 4.46 plus or minus 0.04 billion years old. And also, according to the data from the Apollo bacteria 67215, the crystallization of the age of the Apollo bacteria is 4.4 plus or minus 0.11 billion years. So this rock also provides the lunar form early in the history of the moon, most likely by crystallized from the magma ocean. Next slide, please.
So Cyrus.
Hello, my name is Iris and I will be presenting on the age of the moon. Next slide, please. So, approximately 62 million years after other solids in the universe began to form, the moon formed by impact against the Earth. Assuming that the magma ocean began to crystallize right after the moon's formation, zircon from the Apollo 17 landing site can be used to date the end of the crystallization. Zircon's radiometric clock is difficult to be reset by thermal vents, and the mineral's high uranium content enables uranium-lead dating to be used as well. The photos to the right are of zircon samples taken from South Massif and were used to date the end of the magma ocean crystallization period. The holes in the mineral are from samples taken, and the colored ovals show age in billions of years or gigayears. Using this zircon sample, we can determine that the moon began to crystallize 4.517 billion years ago and finished 39 million years after that.
And we had the lunar cataclysm, which happened about 4.1 to 3.8 billion years ago. And the lunar cataclysm is the reason that the craters are visible on the moon, those very large craters. After that, the dating of the moon and the craters, they've drastically dropped off. Lunar features.
Maria is a dark, leveled, and relatively smooth part on the moon. There are more than 15% of area on the moon is Maria, and as the picture shows, like you can see a lot of Maria on the moon, and Maria is totally different from the Lunar Highland or other terrain, and there are two different type of Maria, and one does is few multi-range circular basins, and another is those few irregular areas, and most scientists and geologists believe that Mars is covered by so few lava flow, and the absolute age are given by radiometric techniques. The ballistic lava flow range in the age from 3.15 to 3.85 billion years. So the episode of lava filling on the moon must have continued for at least 700 million years. Next, please. And from these two pictures, you can see more detail, and like the smooth and dark part on the moon is Maria. Next page, please.
Lunar Highlands. Most of the crust of the moon consists of silicate rocks called anorthosites, and these regions are known as the Lunar Highlands. They are made of relatively low-density rock that's solidified on the cooling moon like slag floating on the top of a smelter.
Audrey.
Okay. Another lunar feature is faults, and the fault scarp or cliff is like a stair step in a lunar landscape, as seen in the images on the slide. These faults are formed when the near-surface crust is pushed together, breaks, and is thrust upward along a fault as the moon contracts. The illustration of lobate scarps that were formed when the lunar crust was pushed together as the moon contracted. This causes the near-surface materials to break, forming a thrust fault. The thrust fault carries crust materials up and sometimes over adjacent crustal materials. Next slide.
John?
It looks like we somehow dropped to 9 participants. So can someone message John? Because it looks like he might have gotten kicked out.
Okay.
since he is not on the current
List. Okay.
presentation. So that is all I can note.
Okay. Well, why don't we go down? Yeah, things are lagging.
Trying to message John right now, if you give me a second.
I've already messaged him.
Oh, Audrey is beating me. Never mind. Do we want to go to the next slide and come back?
Yes.
Okay. Let me have this beauteous image. Okay, wrinkles are very similar to the faults, as that they are formed by the moon contracting as it cools down. They have actually emerged relatively recently, as most wrinkles are about 1 billion years old, but there are some as young as about 40 million years old. The way we can date these wrinkles, if you look at one of the images, you can see craters that form where the wrinkles were. We can tell that they're newer than that. So we can date these wrinkles by dating those different craters, because the smaller craters get filled in faster by the moon. So what happens is we can date it from that. And that's how we can date them to about 1 billion years old, or about 40 million years old. And what happens is they take the form basically of these wrinkle ridges, which can go on for over 250 miles and over 1,000 feet high. That is obviously the exception, not the rule. They're usually a bit smaller, but they're basically these wrinkles that can go on for miles and reach up. And they're that, and they basically obviously form as the moon contracts. And as the moon contracts in different ways, you can see them form in different ways. If you look at the second photo, you can see how different wrinkles have formed in different patterns as the moon has contracted in different directions.
Okay, very good. Was that John perhaps that got on? No? Okay.
John is here. I just don't think he's having issues with his Wi-Fi.
I'm here now. I'm sorry. My Wi-Fi was so bad that I just completely disconnected.
Okay, I'm going to put you on your reels here, John, and wait till it loads in for you and you can present reels.
Okay. There are 3 rules. There are sinuous rules, which are they're pretty much the same as collapsed lava tubes on Earth. They're much larger though, for various reasons, such as different flow rate of lava, less gravity, higher melt temperature, and so they're bigger. Straight rills straight rills are not completely explained as to why they happen, but they're definitely related to faults. And there's a picture of a straight rill on the far left and a picture of a sinuous rill on the far right. And then arcuate rills are flat floored troughs with steep walls and only a few kilometers wide. They're created like similar ones on Earth, and they're called grabens, and they generally occur in parallel sets.
Okay. Good. Thanks for getting back on, John.
Sorry, I disconnected.
Oh, that happens. So it goes. Hey, Cyrus.
Okay, lunar volcanoes. So volcanic rocks on the moon's surface are primarily basalts, which are common on terrestrial planets because of their similar mantle composition. Dome shapes on the lunar surface are shield volcanoes, and typically appear as broad, shallow landforms that are circular or oval. Located on mare basins, these shield volcanoes often have lava tubes or other geologic features surrounding them. Lava terraces are like the shoreline of what once used to be the magma ocean or lava from volcanic eruptions. Cinder cones are collapsed domes and generally have a low albedo, which means they are difficult to see due to low light. Dark haloed craters are broad and low landforms that were created by extrapolation from cinder cones. Next slide, please. Domes versus craters. So when looking at the moon's surface, it is often difficult to tell the difference between a dome and a crater. The best way to distinguish a dome from a crater is to notice how the light hits the formation. By finding the direction of light, it is easier to see the difference because the light will hit a crater on the opposite side that it will a dome, as seen in this picture. Next slide, please.
Okay, lava tubes. They're hollow tubular surfaces on the moon. They're formed by basalt lava flowing underground and a hollow chamber. They can be as long as 500 meters. Longer tubes tend to collapse, and a lot of people believe that the collapsed tubes form the rills, such as the Hadley rill in the photo. They're likely candidates as shelter for future manned missions to the moon. Okay, Audrey.
Okay, another feature of the moon is craters. There are three main types of craters. Simple craters, which look like smooth bowl-like craters, and complex craters, which have flat floors with collapsed walls and a central peak, and multi-ring basin craters. These craters have flat walls with two or more concentric rings, creating a bullseye effect. There are two subtypes of complex craters. There's the central peak basin, which is complex craters with a ring of little peaks around larger central peaks, or a larger central peak. And then also the peak ring basin, which is a complex crater with no central peak, but a ring of massive peaks. And the types of crater morphologies is based on the size of the crater's diameter, with the smallest being simple craters and the largest being multi-ring basins. The morphology classification based on that diameter can vary from planet to planet. Next slide.
Lunar missions.
The Ranger missions. So the Ranger program was created to take the first close-up pictures of the moon's surface for future scientific and manned missions. With the first launch on July 28th of 1964, this program consisted of 9 unmanned spacecraft launched, with 6 failed. The missions were divided into 3 blocks that had multiple missions per block. Block 1 included Ranger 1 and 2, which were both unsuccessful due to launch failure. Block 2 included Ranger 3, 4, and 5, all of which failed because they either missed the moon completely or were disabled upon impact. Block 3 included Ranger 6, 7, 8, and 9, and was overall much more successful than the previous 2 blocks. The Ranger 6 landed and its cameras failed, but the last 3 spacecraft were successful, and with their wide-angled cameras, they collectively took over 17,000 images. Next slide, please. The Lunar Orbiter missions. Beginning in 1966 and ending in 1967, 5 unmanned spacecraft were launched as a part of the Lunar Orbiter missions. They were designed to photograph and determine a landing site for the Apollo missions that were within plus or minus 5 degrees latitude and plus or minus 45 degrees longitude. This is important because future moon missions had to remain in contact with Earth at all times. Although all of these missions went well, there were some transmission issues, and many photos were lost. Overall, the lunar orbiters were largely successful, and almost all of the moon's surface was photographed within 2,600 images. Next slide, please.
It's the Lunar Reconnaissance Orbiter.
Okay, the Lunar Reconnaissance Orbiter was launched on June 18th of 2009. It reached lunar orbit, also known as its destination of the moon, within 5 days. The purpose of it was to provide data which would be used to 3D map the moon to date in higher resolution than before. This map would be used to determine landing sites and other useful information regarding the moon. It got high resolution images which scientists would translate into a 3D map and study and analyze and come up with conclusions based on the 3D map. The Lunar Reconnaissance Orbiter found things like lunar hydration times of the bright side of the moon. The Lunar Reconnaissance Orbiter also demonstrated the first laser communication with a lunar satellite. The major problem the Lunar Reconnaissance rover had during the engineering phase was its large propulsion tank. The distance from the Earth to the Moon required most of the satellite's mass to be fuel, and furthermore, the slosh created by the movement served as a problem. Next slide. The Lunar Prospector was launched in January 16th of 1998. They did this in the hopes, the Lunar Prospector purpose was to map the moon's surface composition, look for possible deposits of polar ice, measure magnetic and gravity fields, as well as study lunar outgassing. Outgassing is when something releases or gives off a substance such as gas or vapor. The Lunar Prospector also did neutron spectrum mapping of the moon. Through this satellite, scientists were able to detect hydrogen on both lunar polars, which is possibly in the form of water. The Lunar Prospector mission ended on July 31st of 1999. The scientists tried to make it crash into a permanently shadowed area of a crater on the moon near the lunar south pole. They did this in the hopes of its crash releasing water vapor that was trapped, but it did not release any water vapor. Next slide.
Lunar image analysis.
Okay, so after, I'm not on the slide yet. After analyzing this image for many hours, we have annotated and marked the image on the slide. As seen on the image, the red circles are simple craters. The lines a crater produces during the impact process withers over time, so the more pristine lines are newer craters, while the faded ones are older. The green line marked is a sinuous rill. The blue shape outlines what we think is either an addition to the rill above or a valley. The orange 3 labeled region has lots of mountains, so we think it's the Lunar Highlands. Also note that the light color is anorthosite, which is less dense than basalt. The yellow 4 labeled region is the Mar. Take into account the darker color and flat surface from the basalt flows. This area is denser than the yellow 3 region, as it is made of basalt, which is denser than anorthosite. Next slide.
This is our second lunar image analysis, and this lunar image includes many geologic features, including craters and domes. The sunlight is coming from the left of the picture to the right and hits the craters on the right side. The craters circled in bright green are more recent than the craters circled in dark green because their rims appear sharper and crisper. These formations are distinguishable as craters because of the ejecta surrounding them that was created during impact. The formations circled in red are shallow domes or shield volcanoes that have a low albedo and are difficult to see. The largest dome in the top left-hand corner of the picture has several features that are found near domes. The purple arrows point to a faint line that may be a collapsed lava tube, and it runs along the darkest part of the dome. Further from the lava tube, the orange arrows point to the edge of the dome, which could be lava terraces. This explains why that part of the dome is lighter than the part closest to the red arrow. Another feature worth noting is the line that the teal arrows are pointing to. This line is the tracks created by the Apollo 15 lunar rover, and it travels from the top right of the picture and encircles several craters. In general, this lunar image contains many interesting lunar features that show the history of the moon's surface. Next slide, please.
This is an image of Hadley's drill, and so the thing outlined in green is a sinuous rill, and it is a collapsed lava tube. And then the thing marked with 1 is debris field from a crater that you can't see, and we know that it's a debris field from a crater because of how the albedo and how much lighter it is. This entire image is covered in small craters, and there's so many that would be just meaningless to circle them all. Dome as it is with the craters.
Okay. Okay, next slide, I think. I can't hear, I think. Okay.
Next slide, yeah.
Next one. Okay, thank you.
Okay, I'll afford image analysis. So the red circle represents the craters, except for the one on the right corner because it's unclear. We don't know whether the edge of it is like a crater or it will continue from the right. It will continue into like a basin. So we mark that as something that looks like a crater rim. So the purple outline represents the purple circles represents the central peak in the two biggest complex craters, and the cyan outlines represent the crater floor fractures on the biggest crater at the bottom, and the green outlines represent the rills. On the top, you can see that it goes next to the region mark number 3 called the impact melt region. So this impact melt region possibly happened because of the impact that caused the largest crater in on the right. And so these green rills are part of the lava flow that goes after the impact happened. The region number 1 and 2 represents the basin in between the the craters, and so the lavender outlines represent the ejecta that's exudes after the impact that caused the crater. You can see that it goes around the crater mark red, the simple crater mark red at the left, and the biggest crater. There is an orange outline in the biggest red circle, and that is we think that is the step terraces of the collapsed material that it is near the rim of the crater. And so during the formation of the complex crater, these materials collapse and form like a step terrace of the collapsed material that's molten from the impact. Number 4, there is another region next to around the biggest crater, and we think that it is the crater rim. So the rim of this crater, unlike the simple one, is very ragged and it's ambiguous, but also because of the formation of the complex crater, the material created this rim, it could be part of the ejecta that's flowing through the ejecta blanket, and also this would cause the immense surface of the area. Okay, next slide.
Okay, Nathan?
I'm here. Thank you. And then here are the works cited. Next, yeah, there we go.
All right. And that concludes the Moon 101 presentation.
Thank you so much. What I'd like to do now is kind of go through it with you and ask a few questions as we go through it. First of all, I should let you know that, that I appreciate all your hard work. You've all clearly worked very hard on this and spent a lot of time. I am a little concerned about time. I do not know if we're going to be able to get through our discussion and the Asteroid 101 and the comments after that in an hour. are you able to go longer, or should we schedule a second meeting? Or just, I want you to think about that. And it might not be an issue, but it might. So I want you to be prepared for that, because it's getting, we're at 40 minutes. So overall, I think you all spoke very clearly. If your bandwidth permits you to share your videos when you are share your video when you're speaking, I think it makes for a better presentation, just to let you know. But I also know that many of you are struggling with bandwidth right now. And I love the use of the pictures and colors, very nicely done. In some of the slides, there was a lot of text where everything was kind of written out word for word. In others, it was more, just a few key words and points. I think in general, things are better if you don't write out everything word for word, if you just have a few words on, because your audience wants to hear you. And if they're reading your slide at the same time they're listening to you, then they're not really listening to you, they're just reading. So yeah, let's start at the very beginning. Can we move all the way back to the very beginning?
And it'll you guys, there we go.
Okay, great, excellent. So next slide. And
next one.
Yes, please. Yes, please. Let's get to the first slide with the contents on it. Lovely backgrounds. And I appreciate the overview of what was going to be presented. That's really nice. Right, perfect here. And I should say, I really appreciated it for those of you who, when you started talking, introduced yourself, saying, "Hi, my name is." That was really nice. And I would recommend that all of you do that for the future. When it's your turn to speak, that you introduce yourself. You say hi and what your name is. That's really nice. For the giant impact theory, different people have called it by different names. Technically, for people who study the nature of science and the philosophy of science, they would not use the word theory here. Dr. Kring, who sort of leads the science behind our program that funds this, has used, I think he uses the word model. So you'll see it written down as a giant impact theory, but technically theories explain really big things. Like the Big Bang Theory explains the whole formation of the universe and all the evidence that supports that. Plate tectonics theory supports everything that we know about not just the positions of the continents, but where the fossils of different animals are and the magnetic lines and all sorts of things. The giant impact model only explains how the moon was formed. It doesn't explain tons of other things. So it might be better termed hypothesis or model. The pros and cons here are good. I wanted to this idea of angular momentum and the moon. Does anyone want to speak to, this is the current most widely recognized and supported model for the moon's formation. There's variations on this model in terms of what size the impactor was. Here, you've written down that it's the size of Mars. When it says the size of Mars, how big is that compared to Earth in this particular slide, would you say?
So like when I was doing research at a lot of models, there were like the moonlets one, and there's like a different hypothesis on the size of the impactor.
Yes.
And so for the would be at least the size of the Mars, because the gravitational interactions would have like allowed the Earth to, like with the hypothesis, it would allow the Earth to like slow its rotation, and like with the position into like with the right angular momentum would allow like the Earth to spin and the moon as when Theia smashed into Earth, I would say that the there's like the model when I was looking it up, there was like the model that of how the hypothesis showed that the materials that was ejected, and as like the impact struck the Earth, it would account for like the Earth's rapid, like during the early stage of the Earth, it was spinning really fast, and so the would associated would like vaporize the a portion of like the ejecta and like the materials that would eventually create the moon.
Mhm.
And so the angular momentum that is now in the Earth Moon system, um, Theia would be like at least the size of the Mars in order to like change the Earth original rotation.
This is perhaps a silly question. Most adults do not know how big Mars is. When you say it's the size of Mars, how big is Mars compared to the Earth, roughly?
It was like it was smaller than Earth, but it was really the size of um of Mars was it was like a close approximation. It was like I think it was roughly the diameter is smaller.
Mars is smaller than the Earth. Do any of the rest of you know how would you say Mars is a quarter of the Earth, a third of the Earth, half the Earth's width? Anyone know?
I would say it's like 1/5 or
I can give the rough gravity.
Say that again. You can give the rough
I
what?
can give the gravity of Mars compared to Earth. I believe the gravity is 2/3. I'm not sure if that applies to the mass, but I know the gravity is roughly 2/3 of.
Mars is half the width of the Earth, and so yeah, most adults in the U.S. don't know, and so I dislike the fact that so many documents out there say that it was the size of Mars, which doesn't help most people, right? Because most people don't know how big Mars is. Mars is about half the size of the Earth. So in some of the earliest models, they were saying that Theia was about half the size of the Earth, half the width, half as wide. Yeah, Mars's gravity is significantly less than the Earth. You're right. It's about a third of the Earth's gravity. So you'd weigh a third on Mars what you weigh here on the Earth. Yes, it could have created multiple moons, but most of the models predominantly indicate one. Does anyone know? So the debris that eventually coalesced to form the moon, which parts of that debris came from Theia? Which parts of that debris came from the proto-Earth? Any ideas there? Was it all Theia? Was most of it Theia? Was any of it the Earth?
It was Theia and also a part of the Earth. So like when I was looking at the debris on the layers, and some of the simulations said that a part of like the Earth's core is also impacted by the hypothesis, and so the debris was flowing to space, and one of the simulations that I look at shows that the debris actually flown back into Earth, and the debris caused impact into Earth and would cause more material to be ejected. And so that's why the composition of the moon, there was so dissimilarity of like the different regions have different rock composition.
Right. There's a lot of scientists who have been working very hard trying to make everything here work out to what we see. You're right. So the idea is that Theia, that most of the crust and the mantle for Theia and some of the Earth's crust and some of the Earth's mantle all went in to form the moon, and that the core for Theia would have probably combined into the core of the Earth. So if you go to the next slide, you can see some of this here. in the slide here where you've got these models where you're seeing, sort of the core of, in that first picture there, in the upper left, it's showing sort of the core of Theia and the Earth, and what's happening and how things eventually collide. And there's multiple models, like you said. So in some cases, it's smaller. In some cases, it's bigger. Robin Canup has done many of these different models, and so you say Canup model over there on the right. The images on the left, those could be hers, actually. I'm not sure. Do you know whose those are? The computer models on the left?
Yes. I looked into like the moon from the papers have a lot of simulations of the impact of the spinning of the Earth and how this hypothesis could have like the aspects of the simulations of the giant impact. So yeah, I looked into.
But the computer model on the left do you know which of the scientists created that? Was that Robin Canup's there on the left? It's okay if you don't know. I don't know for sure. It looks like it might be hers. So she's one of the scientists who's done a lot of the work on modeling different sizes, different speeds. Is it a glancing blow as opposed to a direct blow, and trying to figure out exactly which would produce what we now see in terms of it. And you were exactly right that the proto-Earth would have been spinning very fast. Our days would have been 5 hours long. And initially, when the moon first formed, it would have been much, much closer to us. And so can you imagine looking outside and having a moon that fills up, a huge part of the sky? And your tides would have been huge. It would have been amazing back then. Probably pretty deadly, probably not a good place to live at the time, but anyway, thank you. Let's go ahead and go to the next couple of slides. We'll go through the next few really quickly. I want to let you all know, so the fission theory, in some ways, there's aspects of this that are similar to the giant impact model, right? You're throwing off debris. And so there's a little bit of similarity between the fission theory and the giant impact model. And so there's some people who are still kind of looking at that model, the fission model, but most people aren't. Most people are pretty much settled on the giant impact model, but there's a few who are still looking a little bit at this fission model because of some of the similarities. But yes, it would have had to have been spinning really fast. But I just told you that in the giant impact model, the Earth is spinning at 5 hours, which is pretty fast. So this one has just a little bit of aspects to it that kind of work with the giant impact model. But the next couple of models, the capture model, nobody really, there just isn't enough evidence to support the capture model anymore. Ever since they really started analyzing the moon rocks and looking at the composition of the Earth and the moon and how they compare and how they differ, they've pretty much given up on the capture theory, although we do think some of the moons around Jupiter were captured, and we think that some of Saturn's moons were captured, but we've given up on it for us, absolutely. And then I think there's one more, right? One more model for the moon's formation that we've given up. Fission capture. There's one that's missing from here, but again, those other models, they've been discredited, so they're less important. There's one other model that shows that if the moon formed in orbit around the Earth, and that one's mostly discredited as well. Because again, those identical oxygen isotopes, it wouldn't explain that either. So, okay. Any questions or comments about the moon's formation so far? Okay, the history. Let's get to the magma ocean here. So yeah, this idea that early on we think that the moon might have had a giant ocean of magma surrounding it. Why? Anyone have an idea? Why would it have a magma ocean at the beginning?
Because I think the ocean, like it needs to crystallize, like it needs time to form.
The rocks needed time to cool.
The rocks needed time to cool. Yeah.
It was very, very hot
It
at
was
first.
very, very hot at first.
Sorry for the echo. I think that
Sorry for
happens
the
with
echo.
some
I think that
computers.
happens with some computers.
So
So
the moon would have been very, very hot from all the impacts that were going on in the solar system at the time. There were so many giant impactors, asteroids, comets, debris in our solar system in the very beginning, and that they were constantly hitting the moon, the Earth, the planets. Earth probably had a magma ocean at this time too. So you've got heat from that. You've got heat from the formation. As the planets are forming, there's a lot of heat there. And of course, radioactive isotopes inside of them as well. So there's a lot of sources for heat, and they would have all been really, really hot. And you're right. We think that there's some evidence that the moon started off with this magma ocean, and that evidence is related to the anorthosite crust. Let's go on to the next slide here. I'll try to make this quick. I know that we're almost at the hour. Yes, we think that some of the denser things sank, you're right, and some of the lighter minerals floated to the top, and those minerals are what forms that anorthosite crust that some of you talked about later, absolutely. We don't see an anorthosite crust on Earth. Any idea what's happened to the Earth that we don't see? Is it possible that the Earth might have had an anorthosite crust at the same time? Anyone want to say yes or no, or maybe?
We have much more active tectonic movement from all the different tectonic plates and a much more active environment. So just stuff is more constantly crashing together.
Crashing together and getting recycled and turned over. Absolutely. We don't have a whole lot of rocks from 4.4 billion years ago. Like none. We have some crystals, and that's about it. So yeah, if the Earth had an anorthosite crust back then, and I'm not saying it did, but if it did, it's gone now. But the same thing could have been happening on the Earth. We don't know for sure. Yes?
Next slide.
Yes, please. Yes, please. Yep. This all looks great. So that magma ocean is one of the reasons we think it existed, because we think it formed this anorthosite crust across the moon. And the anorthosite crust is what we're looking at largely when we're looking at the highlands. So let's go ahead and go on to the next slide. Let's continue. So yeah, we think that no comments here to this one. Let's keep going. The Cataclysm. Let's talk really, really briefly about the Cataclysm. We don't know if it was continuous from 4.1 to 3.8. We don't know if it slowed down and then increased at 3.8. The reason there's a lot of craters on the moon visible is not actually because of the Cataclysm. The Cataclysm would have hit the Earth too. It would have been, the reason there's lots of craters on the moon is what one of you just said, that the Earth, of course, overturns its crust. So our crust has been erased. There aren't that many craters on the Earth because the craters on the Earth have been erased by plate tectonics and erosion, whereas the moon has had impacts ever since it formed and continuing. So I wanted to clear that up just briefly. The lunar cataclysm is also sometimes called the late heavy bombardment, and there's evidence that this happened throughout at least the inner solar system, that the Earth, Mercury, Mars, and the Moon all were hit by a lot of really, really big, probably asteroids, around 3.8 billion years ago. So, all right, let's continue. Features. Continue, please. Great deals there about the Mare basalts. You're right. One thing I should say, we can, as somebody mentioned, this idea of dating the moon's surface based on the number of craters we see. There are some places on the moon that show that there might have continued to be a little bit of lava flowing as recently as 1 billion years ago, but small areas. You're right, the majority of these Mare basalts flooded about, around 3 billion years ago. They didn't happen at the same time as the impacts. There's a lot of misconceptions. A lot of people think they happened because of the impacts. They happened afterwards. So the impact left these huge basins, enormous basins, and then the basins had cracks in them, and the basalt flowed in later, not immediately at the same time. Let's continue. And the highlands are indeed a northocite, which is predominantly plagioclase feldspar. Here you say that it solidified like slag floating on top of a smelter. Is that something that's familiar to you? Because I don't have a good picture in my head of that, and I wanted to make sure that that you understand it's related to that magma ocean you showed me earlier with the pictures of the stuff floating up.
We kind of talked about it the other night, but
okay, yeah, we think it's from the northocite floating up. Let's please continue. Faults, everything here about the faults was correct. I love the slides, I love the pictures. I do want to say there's later slides that talk also about wrinkle ridges. Wrinkle ridges are related to faults. You're showing the same thing. The faults and wrinkle ridges are related. And as the slide that talked about wrinkle ridges talked about how the moon, as it cooled, it contracted and formed those. Everything here about the rills is great. You can continue.
okay. And there was the wrinkles.
There's the wrinkles. So yeah, the wrinkle ridges are related to the faults. They're kind of the same thing. And yeah, they form as the moon contracts. As it contracts, as the crust, as the inside contracts and it cools off and the outside is cool, it kind of runs into each other as it's contracting and you get those faults. So, but everything there looks great. Volcanoes, good overview here of volcanoes. Sounds great. Let's please continue. You're right about how you see the domes versus the craters and the coloring and the light and the shadows. That's perfect, but when we get to the lunar images, you guys have a couple of misconceptions about some of the image analysis that we'll have to think about this when we get to. Please continue. Awesome. Good points about the lava tubes. No changes there. I love it. And I love these pictures and how you've arranged the pictures and the text. And a very good overview of craters as well. No comments or changes to craters. Please continue. Missions. Thank you. Rangers, you're right. Great. Continue. Orbiter missions, continue. That sounds good. Preparing for Apollo. LRO, I was a little surprised that you put LRO here, and I was wondering why it's in this order. Any feedback or thoughts?
I don't think we had a particular order.
Okay, I thought that perhaps they were chronological. LRO is still ongoing, and we're continuing to learn about the moon now with it, and so but it's been going around for the moon for quite some time, and it's teaching us more about so many different things. The features, it looks into the shadowed regions at the poles of the moon. It's been examining for sources of hydrogen, evidence of water at the north and south poles of the moon. When the LRO got to the moon, it sent something called L-Cross intentionally, which crashed into the south pole of the moon so they could observe the plumes, just like the next slide where you talk about Prospector crashing into the moon at the end. After Prospector was done, they decided to try to recreate and intentionally have something run into the moon and see what came out. And they did find signatures for water, among other things, at the south pole of the moon. So LRO, chances are if you folks pick the moon and are doing data related to the moon, there's a very good chance you'll be using LRO data for your research project, potentially. Next slide. And Prospector was, of course, before LRO. It was a good mission. You didn't talk about Apollo, which surprised me. Apollo brought back all those moon rocks, which are so key for us identifying ages of things. And yeah, you might need to look at Apollo later at some point in terms of some of the data that we've got. The rocks from Apollo were fundamental for some of our models for the moon's formation and some of those isotopic ratios and things like that. So, and ages for different parts of the moon. Please continue. And we're at 10:07. Are you all okay for us to continue and finish up at least the moon, or are you good for another half an hour? How much time do you all have?
It's 8 p.m. right now, so I think it's fine for me. I don't know about like the others, but yeah, I think I can still go on.
How about the rest of you?
Yeah,
Jeff?
it's fine. I can continue.
I have a lot of homework. I might have to get off pretty soon.
Same here.
Holly, if it's all right with you, what I'd like to do is finish giving comments on this and maybe have you all schedule the asteroid one for another night, if that's okay.
Oh, that's fine. That'd be fine.
And the asteroid one won't be as long. And if you want to, you can really fundamentally focus it on just the pictures that you're analyzing. You don't have to go into everything you've learned. You can, but you don't have to. You can focus on the pictures that you're analyzing.
Okay.
For this picture, I wanted to ask you really, really quickly. You're right about the Highlands and the craters and the Wrinkle Ridge. This is the Apollo 15 landing site. Can you tell right now, so you've got the red crater that's towards the middle, and then the green line for Hadley Rill, and number 3 and number 4. For those 4 items, which one do you think formed first? The Highlands, the Mare basalt, the Hadley Rill, or the crater? Which one do you think formed first? Which one do you think formed last? And, you know, any ideas?
I think
The crater
the
formed-
Highlands formed first, and then the basalt flowed over it.
The Highlands formed first, and then the basalt flowed around it. And you can see where it kind of filled in, like water fills in a bay. And that's called embayment. And so, yes, so the Highlands first, and then the Mare basalts filled in around it. And I heard somebody saying something about the crater?
The crater formed last, which means that green line formed third.
Right. The green line have to form after the Mare because it forms on top of the Mare. So how could you cut a line there without the Mare already being there, right? So yes, so that's exactly right, the order here. So the Highlands first, number 3, then the Mare basalts, number 4, and then the Hadley Rill, and then the crater last. Good points. Awesome. Let's please continue to the next slide. Here, this is actually not Apollo 15. You're right, those are tracks. It's from Apollo 12. And the areas that you thought might be domes are also craters. They're just really, really, really worn down, almost filled in craters. They're old craters. So none of these are domes. They're all craters. And some of, except for the lines there from the tracks from Apollo 12.
Those were tough.
They are tough. They are tough. They're Yeah, it's hard to tell, right? It's hard, especially the light being almost overhead. It's really hard. You're not getting a whole lot of shadows that'll tell you more. So it is tough. You'll notice that the smaller ones tend to be, some of the smaller ones are sharper, and those are some of the newer craters. The brighter the crater, the newer it is as well. Because they, in addition to kind of getting softened as they get older and eroded away by impacts and stuff, they also they darken over time. So the brightest craters tend to be the youngest ones. Last slide. Next slide. We're almost done, I promise, because I know you guys have homework. So this is the last slide we're going to talk about. The slide afterwards isn't one that Andy passed on to me for analysis, so I haven't studied it myself. And you guys did from what I could tell, everything you said sounded good to me. For this slide right here, this is a close-up of that Hadley Rill from Apollo 15. And the areas that you thought were domes, I looked at those and I thought those might be domes too myself, but they're not. Those are craters. There are domes that aren't in this view. They're just above, just north of the picture here. There are some volcanic domes, but the dark areas there that you thought might be domes are actually craters. But I understand why you said that, because I had to look it up myself. Some of these craters you might notice are kind of long. That's when they're secondary craters, when you have something hit making one crater and then that throws off rocks that are at a low angle. Those low angle rocks from a primary impact can create smaller oblong secondary craters. So, and you're right, number one, that debris is debris from a crater nearby. So you guys got that all right. Excellent job. Good analysis, a lot of hard work. We'll make the next one much shorter, I promise. Holly, I'll get back with you and let's talk about when to schedule it, because I know you guys have to go. Holly, this recording is, I'm going to send it to you so you have it. And if anyone has any other questions or comments, I am delighted to hear them. Thank you all so much for all your time and all your hard work. Awesome job, guys.
Thanks, Christine. And our asteroid one is a lot more because.
So, okay. Thank you all. Have a great evening.
Well, thank you, Christine. Okay. Let's see. How do we do this? I go to Ring Central.
You should see a button at the bottom that says share.
All right, share. Okay.
If any of you have the bandwidth to share your video as well, it's always nice to see the people who are talking.
Yeah. So go ahead and show your faces tonight. It's okay. I'm having a very bad hair day, so, you know, I'm sure yours is better than mine. So let's see. So I do have the asteroids. What are you seeing on my screen? Can you see the asteroid?
Not yet.
Okay.
Now we do. Now we do. Yes.
That's right. There's a little lag on this one, if I remember right. Okay. Well, the bulk of the people here, it could be the others had, I know Audrey and John had some robotics, and I don't know, maybe they kind of are late getting back home tonight. Okay.
Nate says that he's having trouble getting his microphone to turn on. Nate, let me try unmuting you and see if that makes a difference or not. I'm going to unmute you and see if you can talk, okay? All right, Nate, I've unmuted you. Can you talk? It doesn't look like it. The other option, Nate, is if you want, you can also try joining. If you you don't know why it's being blocked by the browser, it's probably the type of browser that happens sometimes. I think Chrome works better than IE or Safari. Sometimes IE and Safari can be Firefox can be problematic. I don't know if you want to try joining by Chrome instead, but if not, you're on Chrome. Okay, then I don't know why. Yeah.
Check your permissions on the web page, maybe. That would be my best suggestion.
Yeah. There are a couple of different web pages, and I'm sorry. There's the two links. There's one of the links lets you upload the actual app, and that one is more likely to work properly if your computer will let you upload the app. But if your computer won't, then yeah. We'll let you go ahead and that's fine. Continue to enter things in the chat as needed, I guess, if that's all right with the rest of your team.
And great, Audrey is here, so thank you for joining, Audrey. I didn't see you a couple minutes ago. Okay. Well, Dylan, I'm going to let you just lead us in, reading the intro slides, and then I would guess John and Jeffrey, you did Itokawa? Or is it Stephen?
No, I don't think it's just me.
Okay, so it's Stephen. Is Stephen still on?
Yeah.
Oh, okay. So then once he gets done, it'll be your turn to talk about your asteroid. Then we'll just go on down. Okay, Dylan, give it a shot in your best speaking voice.
Hello, we are St. Mary's Astronomy Club with Dylan Daneman, of course, the kid who definitely knew he was about to present this.
Okay. Want me to, okay, doesn't want me to go to another slide. Okay, there we go.
We are, of course, once again, St. Mary's Astronomy Club with Mrs. Benzel, Audrey Mills, Dylan Daneman, Jeffrey Zhao, John Sagassi, Nathan Lemley, Stephen Hong, Transley, and Zyrus Zaka. And we are here to give our presentation on asteroids.
Okay.
3 main ones, in fact.
Whoa, it's, oh, I must have the wrong, what's going on? It's doing its own thing here, just a second. Okay, so who's doing Itokawa? Stephen.
Okay, so my topic is Itokawa. So here's some basic information you need to know about Itokawa. So Itokawa was first found in 2001 by Golden Stone. Is a Japanese a vehicle or a satellite in the space, and probably the Itokawa was 630 plus or minus 6 meters long and 250 plus or minus 30 meters wide. And Itokawa have been made by 2 smaller asteroids slam into each other due to the gravity. And instead of having craters, it has very rough surface. It is believed to be composed by a bunch of rubber stuck together by gravity. And how it's relative for each other, and how do you know that? With the analyze from the data from the Hayabusa, is a Japanese satellite spring back. It's more likely about 8 million years old.
Okay. And here's a picture of it, of Itokawa with the boulders and the regolith from its formation. Vesta.
Hello, I am Zyrus and I'll be presenting on Vesta. Next slide, please. There we go. Okay, so Vesta is located in the asteroid belt and is the 2nd largest known asteroid. Vesta is similar to the Moon in composition, as it both has large and dark regions. Due to its high albedo, this asteroid is also the brightest and can sometimes be seen from Earth with the naked eye. Vesta is also similar to terrestrial planets because it has a crust, a mantle, and a core, which are unlike other asteroids. This means that Vesta could have been a planet if not for other larger planets. Stretching across the equator are several large grooves called fossae, which are riddled with craters formed by impact. These fossae could possibly be fractures caused by other asteroids that hit Vesta approximately 1 billion years ago. Vesta is believed to have been formed 3 to 4 billion years ago, which is within 1 to 2 million years after the start of the solar system. We know this age because of the order in which different materials cooled on the asteroid's surface, similar to how we know the age of the moon.
And Nathan? Were you able to talk, Nathan?
Nate was the one who said that his microphone isn't working.
Okay, well, I'll go ahead and tell everyone we worked on this the other night. And the yellow line is showing where the fossae are. There's, several others that you can kind of see these kind of groove areas. And the purple shows the order of impact. It looks like these smaller craters, because of the law of superposition, the craters lie on top of the fossae. So the fossae are older. That's why it's labeled a 1. And the craters are labeled 2 because they're younger. The other kind of noticeable feature are the craters, which are outlined in red. And from what we could tell on the ones labeled 1 and 2, once again, 2 is younger than 1 because of how the rims overlap using the law of cross-cutting relationships to superposition. You can kind of tell that the one labeled number 2 is younger. Okay. And Eros.
Okay, I am here. So Eros is the next one I want to go on to. Next slide, please. And Eros is, of course, the 433rd asteroid ever to be discovered. And it is an S-type asteroid, which basically means it's composed of siliceous material. And this is a big deal because we generally assume that these asteroids have been around since the beginning of the universe, but this is a unique deal because we actually tested it, and this is one of them that we can determine formed basically 4.5 billion years ago at the start of the universe, and it's basically material that's just been floating around ever since then, and it's the second biggest near-Earth object, and what it is it's basically that's objects that are 1.3 AUs or astronomical units of the Earth. So that means it is one of the asteroids that is in the Mars group, which means it is following the circular orbit of Mars. And there's a chance, because that orbit is unstable, that in the next couple million years, that it can actually get knocked into Earth's orbit, but we're not sure if that's going to happen. And it was one of the first ones discovered, as I mentioned before, with the 433. It was discovered by Carl Gustav Witt in 1898. And it has a mean diameter of 16.8 kilometers. And so that's one of the first things to know. And it was unique because it was the first one ever to have a probe land on its surface, which happened on February 12th, 2001, as I mentioned before. And this was a soft landing. And so they actually had to land it. It, of course, landed on the Shoemaker crater, which was basically this major crater that happened about 1 million years ago. It was never officially named the Shoemaker crater. What it does is it caused a lot of different effects on the geological development. What happened is, because it was such a big crater, it created a lot of regolith, and it created a lot of the regolith, or the dirt, basically material, is from that, as they found with studies. That's a lot of ejecta. So that's why there's so many ejecta, and it covered up a lot of small craters, all their other large craters, and it's basically this weird bent thing. And it was basically one of the first probes you're ever to take.
Wow. So okay. So here's the diagram. I don't know, is it on, Dylan?
It is.
Okay. So you can see this red circle's the boulder. The number 1 is the regolith, and then the green are showing the direction in which the sun is shining on the surface. Okay. Okay. And
Okay, great. I have a few different questions, but excellent presentation. Let's go ahead and let's start at the beginning, and I promise not to take too long with this.
did you want the slide on?
Yeah. Let's go through the slides again and talk a little bit about some of them and about what you all see for some of these pictures. And while you're getting those set up, let's go ahead. There was one word that was used that many people conflate, the term universe and solar system and the formation. How long ago did the solar system form? Does anyone have any evidence from their research or from the data that we've gotten back from meteorites and asteroids? How long ago did the solar system form?
I can answer this, but I'm waiting to see if anyone else does.
I also have the answer in case anybody else needs it.
I'm mainly saying that because I think I might have accidentally said the wrong word, even though those two are very different.
What's your number?
It's a very common thing though, right? Because we hear people use those terms interchangeably, even though you might know it in your head, the wrong word sometimes comes out. So
I can give the answer for both if you want.
Yes, please.
The universe formed 13 billion years ago, which we can tell basically from the background radiation. And I know the Earth formed 4.5 billion years ago, which dates, and it formed just at the very beginning of the solar system. So we can trace the forming of the solar system to roughly the same time, about 4.5 billion years ago.
And excellent. Although the data that we have for the solar system formation isn't from the Earth. We have no rocks on the Earth that are that old. We have no pebbles, we have nothing on the Earth that dates that age. It's the asteroids that we do, the meteorites from asteroids that give us those dates for the solar system formation. So yeah, but exactly. And you will find many people in the US and around the world who use the term universe, galaxy, and solar system interchangeably. So of course, sometimes in our heads, the wrong words come out when we've got a different picture in our heads. So. Irikawa, great. While we're looking at this picture, let's talk a little bit about, so the surface here that you see where it's got some smooth areas and some bumpy areas, and you made comments about that. Does anyone want to comment, why do some areas appear smooth? What do you think makes some smooth compared to the bumpy areas in other spots? Any ideas?
John, are you gonna, I mean, you kind of researched this one a little bit too. Did you come across anything?
Oh, I'm sorry. Are the smooth parts where it's been hit by something and so it's smooth there because the stuff has been like ground up more, and then elsewhere it's like rubble from it being basically a big pile of rubble?
The asteroid we do think is a rocky rubble pile where the whole asteroid is composed of varying sizes of boulders and smaller pieces of debris. You're right there. And so the areas that are smoother could be filled with the finer ground regolith, the little pieces of debris potentially. There's still a lot we don't know here. We don't know exactly why things are exactly where they are. Some of it also is the gravity field for this thing is probably kind of weird, right? Because it's in these weird pieces, and it's not strong gravity. This is a little asteroid. It's barely being held together by its own gravity. And you're right, when things come around and hit it, who knows, we're still trying to figure out what happens, right? If something comes and hits it, does the whole thing kind of go boing and then settle back down again? So we're still figuring out all these details. There's a lot of questions, more questions than answers, but it probably is finer grained debris, finer grained regolith compared to the bigger pieces. I did hear other people suggest that maybe those could be impact craters. And maybe, but you'd have to convince me of it. I'm not sure. So good point there. There's some different ideas. Do you see how why are the boulders on top of it, on the surface? Why aren't they all covered up by debris? There's a few different models, a few different ideas, and there's one that different people have brought up. Does anyone have any ideas about why the boulders are on the surface as opposed to all being buried? And it's okay if you don't. I've heard several times the description of a model to explain it, and but again, this is a model. We don't know the answer for sure. You know how if you have a box of cereal of different types, sizes, some of the bigger pieces wind up on the top, and all the little pieces wind up at the bottom? Have you ever seen something like that? Or where it sorts out, right? While it's being transported to the store and then to your home. Or nuts, if you've got a thing of nuts, a can of nuts, all the Brazil nuts are on the top and all the peanuts are buried underneath the Brazil nuts. It's called the Brazil nut effect for this reason. And the idea is that as you keep shaking it, the smaller things kind of get to go underneath the bigger things, and the bigger things wind up on top. And so some people have suggested the Brazil nut effect to explain why you've got the boulders on the top here instead of all being buried as they would likely be by debris. So anyway, next slide, please. And there was one thing here. I think that there must be something, one of your sources of information here about the date being 8 million years old. Something there does not sound right. The data from Hayabusa, we think that the rocks and the materials that formed this asteroid are indeed billions of years old, not millions. So I'd have to see the research or the source here for that 8 million years old date, because that just I'm not sure if maybe something happened to the asteroid 8 million years ago, but I'm not really sure that the data from Hayabusa indicates that it's only 8 million years old. That would be remarkably young. That would be incredibly young. So so something there might be off. Yeah, the Hayabusa mission has visited and studied Itokawa. Goldstone is actually a telescope here on Earth, operated, I think, by NASA.
We ran the ones that were in my class last year, and John and maybe Audrey from our club, we ran those telescopes last year and looked at, gosh, did we do the SETI? No, we did, I think, Black Hole Patrol. That's what I've done all of them. So yeah, so that's what Goldstone is. So if they didn't know, it's what we were talking about.
Cool. Yeah, but you're right. The Hayabusa mission is a Japanese mission. The asteroid wasn't discovered by the Japanese mission. A Goldstone isn't a Japanese mission, but yeah. And it is indeed believed to be a rubble pile. So Thank you. Let's go ahead and continue to the next slide.
Oh, and I thought whoever wrote this, they did a good job, you know, bullet pointing it.
Yeah, absolutely.
Do that. So I know it's some bullet pointing happened here. So. All right.
And Vesta. We can go on to the next slide. And no disagreements. Yes, it's huge. Similar to the moon in composition, I'd have to look at that. I mean, it's like the moon, it has basalt flows on the surface, and yes, it does indeed have a crust, mantle, and core. It's differentiated like the Earth and some other planets and the moon. The moon is differentiated, it's got a crust, mantle, and core. The Earth is differentiated, so is Vesta, where some of these other asteroids aren't. Some of the other asteroids were never large enough to heat enough for the materials to cycle and form a crust and a mantle and a core. And it is almost spherical. It would be a lot more spherical if it wasn't for that giant impact on one side. In terms of it potentially being a planet, given the way they redefined what a planet is when they redefined planets, when the International Astronomical Union declared that Pluto wasn't a planet, Vesta would also not be eligible to be a planet by the same consideration. Vesta and Ceres, being in the asteroid belt, haven't cleared their orbits. So, even in spite of its size and in spite of the fact it's differentiated and orbits the sun, it wouldn't be considered a planet, just like the other asteroids in the asteroid belt aren't eligible because of the redefinition. Yep, and it's old. Let's continue, and we'll look at some of the pictures on the next slide here. Yes, good job looking at things like superposition and what's on top of other things. I wanted to point out, do you see some areas here on Vesta that are darker and some that are brighter? And if so, do you have any ideas why some of these areas are darker and why some areas might be brighter?
Well, I wasn't sure myself looking at it, since the dark part is dark and the bottom part is lighter, how much of that had to do with the sun coming from that direction, because it does gradually turn to gray and dark. But there are some patches below the lighter patches that are darker. However, it could be because the fossae are popped out that, I was thinking maybe they're just up hitting more of the sunlight. It's kind of hard to tell.
I believe,
yeah, please.
So thank you. I believe that it's also similarly to how it was created, because it did, if I can remember from my research, have a similar lava flow that is similar to the moon. So it kind of melted into different layers, and some of it is darker because it's a different mineral.
Different composition. Yeah. Very good, very good. Yeah, so over by where you've got the number 1 and number 2, over by those craters, do you see how that area looks a little bit smoother and darker? There probably at some point was a lava flow covering part of that, like a basalt lava flow, just like the basalt lava flows on the moon. And so just like the moon differentiated and the moon has a crust, now the moon's crust is a northocite, and nobody's saying that Vesta's crust was originally a northocite. But we do know that Vesta, in terms of the mineral composition, there are flows that are definitely basalt, and there are lava flows there that are younger than other parts of it. And you can tell over by where the number 1 and number 2 are, there's a lot fewer craters there. So the lava flow there is younger than, say, look at all the number of craters over by number 2, where there's lots of little craters. So good job there.
So we were talking about craters on asteroids Saturday night, and I don't know if Ceres has bigger ones, But are there lava flows and things inside some of these bigger craters on Vesta, or do they extend more to the outside?
I'm not 100% certain, but I think that the lava flow was before the crater that formed number 1 and number 2, because it appears to me that the craters are superimposed on top of it.
Okay.
Although you know, there was another student in a different group who suggested that the lava flow came as a result of the craters, and a scientist suggested that number 1 and number 2 could be a double impact from a single object that broke into 2 pieces and then hit it that way. I agreed with your superposition thing. But a scientist who happened to be listening to one of the talks said, you know, based on the size and the shape and the format, that Vesta has a number of things where there's double impacts, where a parent body broke into pieces and those pieces hit, you know, right next to each other, or, you know, like a stone skipping, and made craters like that. And he was an expert on impact cratering, so that's on Vesta. But yeah, and Vesta, the yellow, the fossae, the ridge there, there's several of them that look like scratches, and they go all the way around Vesta in a giant circle, and it's just amazing. And it might very well be related to that giant impact that surely kind of almost came close to shattering this huge asteroid, because the impact took a giant chunk out of it. Kind of looks like the Death Star in some ways. I mean, that big.
I do believe that the craters would have come after the lava flows, because I think I did read somewhere that the other asteroid that impacted Vesta and created the like fossae and the fracture marks probably would have contributed to the lava flow and like created a molten surface on Vesta.
Awesome. Great research there, because yeah, you can see this poor little, well, not little, this poor giant asteroid has been badly dinged up. Awesome. All right, let's go on to the last one.
And this picture's four pictures compared to the other. I'm sorry, 4 arrows. Although, Dylan, I was impressed by the amount of information.
I like the information here about all of this. Let's go to the last picture. And I had a question here. There was the excellent observation of the direction of the sunlight. Does anyone want to comment how you know that?
You can, I kind of just looked the shadows. I could tell, well, they were rocks. And it was the gradient that helped show they were all pushing up instead of going into the ground because of the way the radiant was. I'm trying to remember what I used to judge it. I kind of forget.
But yeah, the shadows, and a great observation, because this is one of those pictures, when I look at it, my mind refuses to process it. My mind has a lot of trouble seeing what these actually are. So excellent job. The bold, and one thing I have heard Andy tell other teams, the boulders can be considered part of the regolith, but you're right, that there's the finer grained regolith and there's the bigger boulders, but the boulders can be considered part of the regolith in that there isn't, regolith can be small pieces and bigger pieces too. And Eros is a pretty small asteroid. So like the first one, it's probably also a rocky rubble pile. We've found that some asteroids are solid, like Vesta, and some might be 1 or 2 or 3 pieces, and some of them seem to be lots of little pieces all stuck together. So that
have a break-off on size as to whether they would call it a boulder or regolith, or they just want to be like, you know, as a geologist, I have a certain size range in mind for like regolith And
I don't know if it's well defined or not. I do not know the answer to that. I think that calling things boulders is just fine, and calling things that are finer grained regolith is just fine, as long as you're aware that bigger rocks can also be considered regolith in terms of the definition of regolith incorporates rocks as well as finer grained materials. That's all.
The thing on Bennu, and one of the, you know, was like, I don't know, there's something I think is really big, so I did, they would incorporate that as, or they would differentiate it out. And okay, so that was, they just said this thing is so big, and you know,
someone asked me once in an interview to define how big or small something has to be a meteoroid versus an asteroid. And, you know, it's, to me, meteoroids are usually smaller than a toaster. and asteroids are, you know, usually bigger than a car. But there's, yeah, you're gonna struggle to find any one person who claims to have the exact cutoff from one to the other. Yeah. Anyway, great job, all of you. I know that this has been a lot of work, and I appreciate it. Do any of you have any questions for me? I know that your mentor is meeting with you and will be able to answer questions as well. But is there anything that I can help answer at this point?
well, I would be interested. And oh, thanks everyone for showing up tonight. I really appreciate it. Even though you know, the bulk of it was just, there's only 3 asteroids, so they were, you know, they were assigned to just, you know, fewer than the whole group. Those of you that weren't presenting tonight showed up, and so that's really good anyway, to support your team, and you know, and just help out and see what's going on. This Saturday night, I sent you a thing, but we'll just mention it again. Our mentor is Dr. Ryan Watkins, and she seems to be like really nice. And she's not one of those that says, oh, I know everything. She says, I know how to find the answer. You know, if we want to do this, I will go and find the resources. So what we would like to do is look at that, what we talked about last Saturday night. I sent you the recording, so you kind of know what we're thinking about for presentations, because we'll talk a little bit about craters and do some things like that the first hour on Saturday night, and then when she gets her kids put down to sleep, she will join us, and what she